Okay, so it should be recording now. Switch to the whiteboard. Okay, so you're seeing the whiteboard, so I believe it's recording now. So we're gonna go ahead and never know if this thing is recording. I wish it would say somewhere. Yeah. All right. So theory, right? So that's the idea. So this lecture, I guess, is under the name. I think I called it on Brightspace. I called it computing gradients and the losses theory. Okay, so we're gonna focus. If I'm, we're gonna go back to the code that I gave you guys, for the Sci-Fi challenge, and we're just gonna focus on 2 lines of code. Amazingly, right? And TensorFlow is just 2 lines of code, but that's huge. That's like the thing that's very complex and everything. There's a lot of algorithms. So that's where from our code, we kind of hand it off to TensorFlow. Do you guys see how that works? It's like almost like this is what TensorFlow does that makes our lives so much easier, because if we had to do all of this from scratch, it would be a lot of work, right? It used to be this way, but we need all the efficiencies that TensorFlow provides, the speed, everything. And so those 2 lines of code basically cover a lot. All right, that's where we hand off things to TensorFlow. So the topics for this discussion, and this may take longer than just today's lecture. As I said, it's mainly a lecture type of thing, but so it may take a bit longer, but I'll see what I can do. I don't want to rush this one. But the topics are optimization and a calculus example, just just because that's what does it for us. Okay, that's what does it for us. And so we got to understand how, calculus does the solution. We're going to talk about the losses that are available, right, for deep learning. I have an example of calculating gradients in Jupyter. And so I have a Jupyter notebook on the GitHub using TensorFlow. So we're going to do that. And then the topics are just the intuition of linear regression, logistic regression. Those actually are you understand linear regression and logistic regression, you understand 60 to 70% of a deep neural network, okay? Because they're very similar. They have common similarities. And so it's like you look at linear regression. Well, we looked at the perceptron already. Then you look at linear regression, logistic regression, multi-layer perceptron, a deep neural network. They're all adding a little bit from one level to the next. Then, as Gangrok said, cross-entropy, right? Cross-entropy is essential for supervised learning. And so we're going to look at what that is. We're going to look at it in the comparison to MSE, which is the mean squared error. Then we have the chain rule, and that's something else that I'll kind of just throw at you. It's just a trick, I guess, that allows the computations to be done. And then there's the question of why optimization for deep neural networks is what is called non-convex. So hopefully I'll kind of try to motivate where that is coming from and provide some context for it. Okay. So as I said, I'll go through this a bit slowly. Okay. And also I should say that on the GitHub, I have like a book or course notes that I've written. Okay, so it's a PDF. You can always reference that. It's chapter 4, basically, what I'm discussing right now. So you can get it from there. Should be on the main STEM repo, I believe. That's where I put it. All right. So optimization, right? So that's basically what we're doing. So at the end of the day, all of this is something called optimization. This has been under several areas like operations research, industrial engineering, over many years, right? Those have been the fields that have done optimization. And then in neural networks and AI, optimization is just the tool that is used to learn the weights. Because as you guys know, we have a neural network. It's got parameters, which are the weights and the biases. We could randomly pick them and just try with every random sequence to see what we get, right? And over time, maybe we would arrive at the optimal answer, right? What's the problem with that? It would take a period of time probably longer than the span of the universe, right? So, it would take too long, right, to do that. If we just did it randomly. If someday, like in 10 years, we have quantum computers or whatever, then maybe, there will be a new approach, right, to do this. Because quantum computers can maybe do all of this all at once. But until then, we have to have a smart way of doing this. So you saw in the perceptron already that we were updating the weights, right? So you guys remember that. And we were updating the weights in a specific way. But if you remember, I told you guys that updating the weight basically meant adding or subtracting a value, and we needed to know what to do. Okay, do you guys remember that? We needed to know if we needed to add or subtract. That's what we're going to talk about today, basically. Okay, so let's talk a little bit about optimization. So I wrote that down here. Let me change it to red. All right, so optimization is a key process in machine learning. Basically, any supervised learning algorithm needs to learn a prediction equation given a set of data, right? So that's the idea. We have the prediction equation. This prediction function usually has a set of parameters that must be learned, right? So remember, in essence, in machine learning, we have two equations, okay? One is called the inference equation, and one is called the loss function, okay? These are the two things that are kind of playing a game together, okay? So the inference, as we have learned in neural networks, starts from the wx plus b. And remember, this just denotes that it's a vector of x inputs and w weights. Make sense? Now, remember that for it to be a, for it to learn nonlinearities, it needs to run through a function, correct? Do you guys remember that? And then this, if we call it y hat, then in the context of linear regression, the most famous loss function is called the MSE, right? The mean squared error, right? So we'll kind of go over that. But that just means that we have a sum of errors from I equal 1 to n, where we take the difference of that predicted y hat, and what? What do we compare it to? Y true, exactly. And we square it to get rid of the negative effect that we might have, because we really just want the distances. Does this make sense? So these are the two equations that if you ever get lost or confused, just go back to this. Even though this is only for linear regression, this is what you can build on top of. All right, so it's good to start here. All right, so we want to learn those parameters, right? The W's basically and the B's that we were talking about. So the question is, how do you learn these parameters, right? How do you learn that efficiently? And the answer is that you do this through optimization. Okay. In the simplest form, optimization consists of trying a set of parameters and seeing what results they give you, right? And initially, the parameters are going to be random, so the results are going to be pretty bad. That's why you always see the loss going down in the beginning, right? But sometimes it immediately, improves, right? So the loss really goes down, so the weights are, that means the problem is basically very easy. So if the result is not good, the optimization algorithm needs to decide if you should decrease the values of the parameters or increase the values of the parameters, okay? In general, you do this in a loop, increasing or decreasing until you find the optimal set of parameters. But the question, as I've stressed before, is, how do you update the weights? Should you go up or should you go down? So as it turns out, we have calculus to help us out. So I will give you, so going back to the idea of the inference and the loss, there's another thing that helps to understand this. Right, so I'm just going to use MSE right now. So this assumes a linear regression problem, probably. Okay, and so the loss function is denoted usually by J, so you will see that as a common thing. And so I'm going to take y hat minus y squared, the sum, right? So there's, besides the equations, we also have a graphical interpretation. So what that means is, just like there's two equations, right? When you're doing this optimization process, there are two graphs that you can imagine in your head, right? There are two graphs that you can imagine in your head. One is, imagine that the problem here is only like, if it's linear regression, what are we doing? I have some data and I'm going to fit a line, right? So I'm going to fit a line through this, right? What is the definition of a line? Y equal mx plus b. So as you can see, the intuition right there is that, right? So you know what a line looks like. It's a straight line. And then you just have to learn these parameters, the w's and the biases, which are the parameters basically, and you fit the line. If it's a classification problem, it's still a line, right? I'm going to erase it. Oops. Erase. And I'm going to now say, you've got purple ones, and then I also have red ones, right? And now the goal is to create another line, but this time the line, you don't want the line to fit through the points, right? Instead, what do you want? You want a line that best separates between the points. Do you see that? But it's still a line. So it's still like the mechanics of it are the same. It's just that the objective is a little bit different, okay, of what you're trying to do. So anyway, either one works. So either that or the fitting a line through the data, okay? Both are kind of related to this idea of the inference and creating this equation. However, there's a second visualization that we can do for this equation over here, all right? So in this equation over here, the one that allows you to compare the predicted to the result, called the cost function, the goal that we have is to do what? We want to do what is this, first of all? What would you call, generalize this to one word? The y hat minus the y. What word could you use it to denote what it is? What is it? Y is the predicted value. Y hat, and the other y is the real value, right? So you're comparing predicted to real. Yeah, what is it? The difference, yes. Okay. What do they represent? Like if you look at all of them together, they represent the error basically, right? So this is sometimes called, or a lot of the time, if you want to call it as one term, the error. So then what do you want to do? You want to minimize. So this should help you to think about what the objective of this cost function is, which is basically to minimize the error. Does that make sense, guys? You want to minimize the error. So we know that graphically, we can have one axis that is the error, all right? Or I'm just going to denote it with J because it kind of symbolizes the whole thing, but it's the cost, the loss, the error. We want to minimize this, okay? So on the y-axis, we have that. So basically, you can think of it as from 0 to 1, okay? And we want this to be as low as possible, okay? On the x-axis of this, we're going to, oops, that's a terrible. All right, so on the x-axis, okay, we need, so what we're learning is, so this loss is in terms, obviously we don't care about the loss function per se, right? The thing that's going to get you $1 million, right, is this one. right? This just helps you to get this one, right? This is the one that you want because you know that you're going to give it some values and you're going to predict something. Do you guys see that? So really, the one that you care about is this function, not this one. But this function depends entirely on these parameters, right? The weights, right? And so on the x-axis of this chart, that's what we denote, the weights, okay? So you can just basically say W. Do you see that? So if W is very low, you know, that's gonna modify this function, and then this function produces something that you compare it to the real, and maybe it's good or bad. Do you see that? And so then you need to decide if you're going to increment or decrease the W. That's the idea. So what do you need? You need something, and this is really important for you guys to understand, that captures the relationship between this, right? Between this. And so that's what this equation does. The y minus, or the y hat minus y squared captures that relationship between the given W and the cost. And as it turns out, this equation can be represented with a graph, okay? This is literally a quadratic function, all right? As you learn in algebra, and that means it kind of looks like that. Do you see that? So what I'm saying is, you pick a loss function, right? So you're going through like a list of loss functions, and you pick one. And let's say you pick this one, MSE, boom. It looks like this, always, and it's unchangeable, okay? So that means, given W's, they only live in this universe of this curve and nowhere else. They don't live here or here or here. They only live in that curve. You change the W, it can only change in this curve and nothing else because of this equation. Does that make sense? This is important because in terms of optimization, your objective is to get there, right? Because if you get this W, when it hits this curve, results in that loss. And that loss is the lowest loss. If you pick a W here that hits there, it hits that loss. So if this is W2 and this is W1, which one is better? W1? Are you sure? Or W2? Which one's the best?
Oh.
Yeah.
W2.
W2, right? Yes, because it minimizes the loss. Do you see that? So this is what is going on. So you define in your architecture, right? Your neural network, this one for sure. Yes, you define it. And you define this one for sure. Very conveniently, we just go to the atom optimize or the opt, and we say MSE, boom. And so you have now picked this one and this one, which basically means you've designed like this universe. And that's the only place where the W's and the J's have a relationship. And so now all you have to do is through stochastic gradient descent, you have to find the optimal, right? So you pick one of these at random. Let's say that you start here, boom, that W, whatever it is. And now you're here. What would you want to do to the W? What would you do? Remember that we have an update weights rule, right? Where we take the weights. So we had something like this. Weights equal weights minus, what was it? Learning rate times something, right? Some delta, something. This delta is what needs to come from this, okay? That needs to come from that. We need to have a technique. So that technique is called stochastic gradient descent. So imagine we use the stochastic gradient. So we've already defined that we want this equation and this equation, right? Which means we've already defined that this is the curve that we end up with, right? And so now when you do stochastic gradient descent, you know that you pick randomly a W, it puts you here. Intuitively, you know you want to get down here, right? So what you do is you should decrease W so that you start going down until you reach the point. And at that point, you found the optimal. Does that make sense? So you're basically decreasing that W. Yeah, because here W might be 3, and then here W becomes 2, for instance. Oh yeah, please.
So I was just wondering.
That's right. Exactly as you said. So in this function, this is a function, correct? So we take the derivative of it, and basically the derivative gives you this slope. And that's the parameter that helps you to determine what you should do. So it gives you a slope like this, or if you're on this side, it gives you a slope like this, or if you're at the bottom, it gives you a slope like that. So that's 0. And one is positive, one is negative, basically. And what that translates to is that you just take the derivative, and that becomes this value right here. So if you're on this side, right, then boom, negative. If you're on this side, guess what? Boom, positive. If you're right here already at the bottom, what do you get? 0. Boom, 0 times whatever, 0. You're already there. What happens to the weights? They don't get updated. Does that make sense, guys? Is this intuitive enough? And that's how you do it. Exactly right. Exactly right. So we want to figure out, what was the learning rate? How did you determine that one? What was the learning rate? Yeah, exactly. By you ballpark it, right? By experiment. But you do know one thing: if the learning rate is too big, it might not converge completely. If it's too small, like 0.000, it'll take forever to get to because think of the intuition. It's like a very tiny step. It's like it can take hours just doing this, right? And if it's too big, what can happen is it starts to jump like this, and it never reaches the bottom. Got it? All right. So as you said, very good. The mechanism that allows us to make this very intelligently or quickly is that we take the partial derivatives of the function given the variable at that point in time. And just mathematically, we always get either what is called the slope of that, which is either a positive, a negative, or a 0. And that's really what we care about, because we want to know in which direction we're going to go. We let the learning rate actually determine the step size. Okay? Any questions? I'll do a lot more than just this, by the way, but any questions? That was a very good question. Nope. All right. So I wanted to give you this idea first. Now, I want to stress this curve that you see is more for intuition than anything else. Unfortunately, deep neural networks don't have curves like this, right? They don't have MSE quadratic. Well, because let's jump to a new one. I'll ask you this intuitive question. What's the guarantee? Let's say that the loss function, right? Remember, there's always an inference function and a loss function. For MSE, definitely it looks like this. But what if all loss functions look like this? What's the guarantee that we have when all loss functions look like that? There's a guarantee. What is it? Huh? There's one minimum. Very good. There's only one minimum. So you're almost like theoretically guaranteed to arrive at the perfect minimum. Unfortunately, deep neural networks don't have that guarantee. And that's where we get to the idea of why are deep learning algorithms non-convex? So what I mean by that question is this is convex. Convex just means bullshit. Of course, it had to be a more complicated term than bullshit. So it's called convex. But this is what this means, right? Convex just means it looks like this, like a bowl. You're guaranteed to get to a minimum. But deep neural whole video
Progress.
So it's recording again. All right. It's recording, right? All right. So I'm just gonna. We probably lost the whiteboard too. Yeah. Okay. Yeah. So as I was saying, so this is mostly a theoretical discussion today, but it's still pretty important. I do have some code examples, so we're going to go through it of derivatives, gradients, and all that. So we'll cover that. So as I was saying, deep neural networks are not guaranteed to be convex. So what that means is, whereas MSE, like for linear regression, is guaranteed to look like that, which means you have only one minimum. Deep neural networks, or deep learning, are non-convex. I'll just say convex, unfortunately. And what that means is that they basically can have multiple local minimum, and there might be one global minimum, but you're not guaranteed to find it. Okay, so a lot of research goes into this, but the idea is something like this, right? That's what that means. Try this, take 3. All right, so non-convex then, as I said, the classic example that you see, I'll do a second example of this. It's a little bit more like connected to a neural network and some math, but this is more intuitive than